This study addresses the efficient sampling of rare events known as transition paths, which connect metastable states in complex systems. Understanding these transition paths is crucial for revealing mechanisms in molecular processes where direct observation or exhaustive simulation can be prohibitively expensive. Traditional molecular dynamics approaches struggle to adequately sample these rare but important events due to their infrequent occurrence. The authors propose an enhanced sampling method based on transition path shooting, incorporating a strategy they call shooting from the top. In this approach, new trial transition paths are generated by selecting points along previously accepted trajectories within a defined shooting range. These trial paths are then accepted or rejected according to detailed balance conditions implemented through a metropolis criterion, facilitating efficient Markov chain sampling of transition paths. By selecting a shooting range that lies between the two metastable states and iteratively optimizing it, this method aims to produce representative and statistically correct ensembles of transition paths. Overall, this technique promises to accelerate the generation of meaningful trajectory data, thereby deepening our understanding of dynamical processes in chemical and physical systems. Figure 1 schematically illustrates the core concept of transition path sampling via shooting from the top. In this depiction, a recently accepted transition path, labeled X and shown in cyan, and a newly generated trial path, labeled X0 in red, are placed against a two-dimensional free energy landscape. On this landscape, dark colors indicate areas of low free energy, and the two metastable regions A and B are marked by white outlines. Central to the shooting approach is the shooting point, indicated in green, that lies on both trajectories within a defined shooting range bounded by dashed yellow lines at Q of x equals Q0 and Q of x equals Q1. For these two paths, there are different numbers of points within this shooting range. N equals 3 for the accepted trajectory, and N0 equals 5 for the trial trajectory. The metropolis acceptance probability moving from the former path X to the trial path X0 is the ratio 3/5, or 60%. Conversely, the acceptance probability to revert from X0 to X is 100%, since the number of points inside the shooting range for X is smaller than that for X0. This careful balance ensures that the generated sample respects detailed balance, allowing correct statistical sampling within the connected transition path space. By iterating this shooting process, a representative ensemble of transition paths can be generated, capturing the dynamical behavior of transitions between metastable states. Figure 2 provides a top-down view of the potential energy surface V as a function of two coordinates x and y. On this landscape, the two stable states A and B are clearly delineated as regions where the potential energy is below 0.1 times the barrier height B. State A is located near the coordinate -1, -1, whereas state B is located near 1, 1. The figure shows three different shooting ranges used to generate transition paths, delineated by colored borders: red for a narrow shooting range, magenta for a misplaced shooting range, and cyan for a regular shooting range. The regular shooting range covers the full area outside of states A and B, as indicated by the cyan boundaries. For illustrative purposes, a sample transition path produced by overdamped Langevin dynamics is shown in blue, indicating a typical traversal between the two states. Different choices in defining shooting ranges can significantly impact sampling efficiency and accuracy. For example, the narrow shooting range is defined to be only 0.1 units wide and is centered around the dividing surface, while the misplaced range is offset in a way that makes it less optimal. These variants serve to study the sensitivity of transition path sampling results to the selection of the shooting region, thereby guiding more effective sampling strategies. Figure 3 presents a comprehensive comparison of transition paths sampled through the shooting method against those derived from long equilibrium simulations, validating the approach. The system uses overdamped Langevin dynamics with a barrier height of 3 kBt, time step size of 0.01, and diffusion coefficient 0.01. Panels A and B show normalized spatial probability densities P of R:TP for transition paths obtained from equilibrium trajectories and from the shooting simulation, respectively. The path of steepest descent from the barrier is indicated by a blue dashed line in both panels, providing a reference for typical transition routes. The shooting range used in the sampling is marked in red in panel B. Panel C plots the difference between these probability densities, revealing minimal deviations, which the authors interpret as excellent agreement between shooting-based and equilibrium sampling methods. This conclusion is quantitatively supported by low Kullback-Leibler divergence values ranging from around 0.0019 to 0.0038, indicating nearly identical statistical distributions. Finally, Panel D displays normalized histograms of transition times, P of TTP, also showing consistent results from both approaches. This close reproduction of both spatial path distributions and timing statistics across different shooting ranges and barrier heights evidences that TP shooting can accurately replicate the equilibrium ensemble of transition paths. In Figure 4, the authors analyze the efficiency of the shooting procedure by breaking down 200,000 Monte Carlo shooting attempts into accepted trajectories, rejected attempts, and occasions where no transition was generated. This decomposition is examined as a function of the choice of shooting range, with parameters set to a barrier height of 10 kbt, a time step of 0.03, and a diffusion coefficient of 0.01. The figure reveals that a misplaced shooting range can significantly impair efficiency by increasing the frequency of rejections or failed transition generations. To mitigate this problem, the authors developed an adaptive algorithm that iteratively optimizes the shooting range location. After a fixed number of shooting attempts, it first tries to narrow the shooting range to increase acceptance. If this narrowing does not improve performance, the algorithm attempts to shift the shooting range to better overlap with regions conducive to transitions. This approach aims at retaining correct statistical weights while improving sampling efficiency, ensuring that the algorithm effectively explores the transition path space without being trapped in suboptimal shooting setups. The figure thus demonstrates the critical importance of properly tuning the shooting range for successful and efficient transition path sampling. Figure 5 demonstrates the iterative optimization of the shooting range for enhanced transition path sampling efficiency, specifically for Langevin dynamics with a barrier height of 2 kbt and a collective variable defined as Q equals x plus y. Optimization attempts occur every 50 shooting shots. Panel A shows the evolution of the shooting range center and width over the course of the optimization, highlighting initial, intermediate, and final steps labeled 0, 8, and 17. Initially, the shooting range is misplaced between -1.5 and -0.5 in the Q coordinate. Panel B tracks the probability of generating valid transition paths and their acceptance over the optimization steps, illustrating improvement as the shooting range adjusts. Panel C overlays the shooting range boundaries at these stages on the two-dimensional energy surface, displaying the shift from the initial misplaced red region to an intermediate blue range, and finally to a well-placed green region. The authors interpret these results as evidence that their algorithm successfully guides the shooting range toward optimal positions that maximize both the probability of proposing transition paths and their acceptance, thereby improving sampling efficiency while maintaining the correct statistical representation of the transition path ensemble. In conclusion, this work demonstrates that transition path shooting, with carefully defined shooting ranges and a metropolis acceptance criterion, can effectively and accurately sample transition path ensembles between metastable states. The approach matches equilibrium simulations in capturing spatial and temporal statistics of transitions, as evidenced by low divergence in distribution comparisons. The authors emphasize the critical role of selecting an appropriate shooting range, noting that misplaced ranges degrade sampling efficiency. To overcome this, They introduce an adaptive algorithm that iteratively adjusts and optimizes the shooting range location, markedly improving acceptance rates while preserving detailed balance. These methodological advances make the transition path shooting approach a powerful tool for probing rare events in complex systems where direct sampling is challenging. The insights and algorithmic strategies presented here offer a solid foundation for future applications in chemical physics and related fields where understanding transitions at the molecular level is essential.